Hello guys, in this lecture I'm going to solve the forward dynamics of this planar manipulator, and I will only consider the first 2 degrees of freedom. So I'm going to be writing a MATLAB script and a tutorial basically for obtaining the dynamics of this manipulator. So if I let go basically of this 2DOF planar manipulator, and assuming this guy is operating in a vertical plane, meaning gravity is acting downward, I'm going to be able to see how this multi-link system will actually wobble as a result of the dynamics that are actually happening. So the way we're going to do this is we're going to use Lagrange. We're going to find the total kinetic energy of the system, and we're going to find the total potential energy of the system, and then we're going to differentiate Lagrange symbolically to be able to find the accelerations on the first and then second joint. And then once we actually obtain the accelerations, what we can do is actually we can integrate these numerically. And once you integrate the acceleration, you can find the velocity. If you do that one more time, you can find the position as a function of time, and there you go. Now you actually have your movement as a function of time. So what I will do is, so this is my MATLAB script is open here, and my command window. So I'm going to begin by, writing my name. And then what I will do is we're going to write a brief description of the program. So this is a forward dynamics of a 2DOF planar manipulator. Right, and then we said the first thing that you have to do, so every time we're going to program, you're going to clear the command window, then we're going to clear any figure that we actually have open, and then we're going to clear any previous variables. All right, so just a recap, what are we doing? We're basically finding Lagrange, and we said Lagrange is equal to the total kinetic energy of the system minus the total potential energy in the system. Right? Well, how do I find the total kinetic energy of the system? So we can say we have 2 links, right? And then we said the kinetic energy in this link is equal to 1 over 2 m velocity of the center of gravity. So if you decompose the velocity of the center of gravity into Vx and then Vy squared, right? We can basically obtain, or we can differentiate the position, right? And then we can get the velocity here and then up there. So this is just general equation for Lagrange. So in order to do that, obviously we need to have the position. So how do we have the positions? We're going to use our homogeneous transformations, right? So what I will do is I'm going to define my frames, right? And let's do that. So I'm going to do HO to another frame, and let's call actually frame G1, right? So this is a frame that actually ends at point G1, right? And it's basically just like X1, Y1. So I have another frame that is actually at point G1. So I can actually use the frames to be able to obtain the position of point G1, right? Or if you want to quickly look into it, basically X of G1 is equal to L over 2, right? L1 over 2 cosine theta 1. So let's do something as well. I'm gonna define my symbolic variables. I'm gonna do syms L1, L2. I have theta 1, theta 2, and the derivative of these, we're gonna see and need them a bit later. And then we have actually alpha 1 and alpha 2. So basically, I'm symbolically defining dimensions of the robot, angular positions, angular velocities, and angular accelerations, which we'll use in a bit for Lagrange. So let's begin by writing our homogeneous transformation. And here, basically, we have to have obviously our rotation transformations, right? And then quickly, these are ROTX. This is nothing but a homogeneous transformation, a 4x4 rotation about X. So simply, I'm adding another row, and the last column is all zeros except for 1. So all of these are, this is rotation about Y. These are all are included in our course, and then these are basically standard. So H01, right, is equal to what? So I'm basically rotating about Z by how much? By theta 1. And then I am translating along X by L1 over 2, right? So let's quickly run that to confirm it. Okay, let's actually, so clear figures doesn't need to apply now because we don't have any figures yet. All right, so there you go. So this column, right, is going to be the position of my point G1, right? So this is how I can quickly capture the position of the center of gravity. Well, this one is a simple kinematics, but if it's more complicated, then your transformations will actually help you a lot. So x of G1 is equal to H O G1, right? First row, fourth column, and y of G1 is equal to what? H O G1, second row, fourth column, right? So now we have these. That is y of G1. Okay, now let's go ahead and then let's actually find HOG2, right? Because we're interested in the position of the center of gravity of the second leg. So what I'll do is, what is HOG2 is actually equal to HO1. Well, what is HO1? HO1 is homogeneous transformation to frame 1, which is here. Let me actually just do it like this. So HO1 is equal to what? So rotation about z by theta 1 multiplied by translation along the x by L1. So here we are at HO1, right? So we're here, right? Then what we're doing, we're rotating about z one more time by theta 2, right? Then you rotate about z by theta 2, then you translate along x by how much? By L2 over 2, okay? So now we actually have the coordinate of the second center of gravity. So I can quickly, so let's actually command that, coordinates of G1, or of the center of gravity of link 1. So what is xg2 is equal to HO G2 1 4, and y of G2 is equal to HO G2 2 4. Okay, well, let's run that. Okay, let's see what's xg2. Okay, we can actually simplify that. Okay, so does it make sense? Well, okay, coordinate of the second point is L1 cosine theta 1, so we're here, right? Then we're basically adding L2, right? Cosine theta 1 plus theta 2, right? Which makes sense. Okay, great. So yg2 should be this one, but instead of the sine, cosine should be a sine. So simplify yg2. There we go, right? So we have it all right, simply with very few lines. So what we can do is now let's go ahead and let's obtain the velocities, right? So x component of bx g1. So if I'm trying to find the velocity of x, or the x component of point g1, right? So what I have to do is basically I have to apply the chain rule. So this guy now is only a variable, a function of one variable. So what is v, or let me actually call it vg1 x, let's call it like that, right? So velocity of point g1 in x direction is equal to what? So it's actually nothing but, so I can do the partial derivative of xg1, right? And I will do that with respect to theta 1, right? But then I have to multiply that by omega 1, right? Because if you're doing that, if you're doing the derivative of this multivariable function, we remember, take the partial derivative, then you have to multiply by theta 1 over dt. So that is why we actually do that. So there you go. So this is actually your velocity, right? So minus L1 sin theta 1 prime times theta 1 prime, which is omega 1. Okay. So let's just call it velocities, right? So velocities of xy velocity of g1 y is equal to diff x g1, so y g1 theta 1 multiplied by omega 1. Okay, so this is that. Or let me include velocities, the center of gravities. So here basically we're simplifying the velocities of the slip pairs on all the links, right? So now let's actually look at how do you find the Vx of point G2, right? So let's look into Xg2. What is Xg2? Xg2 is, it's a function, it's a multivariable function of theta 1 and theta 2, right? So how do you get that? So Vg2x is equal to, so you do the partial derivative, right? So diff x G2, first variable, multiplied by omega 1, plus you do it one more time, right? Diff xg2 second variable multiplied by omega 2. Okay, and then the easy part here is basically I'm going to do it one more time so I can obtain that in the y direction. So yg2 theta 1 omega 1, right? And then where this is a derivative, right? Time derivative of this variable. yg2, okay. Great, so let's just run it and let's see what happens. Okay, we're good. Simplify v simplify vg2y. It doesn't get any more simple than that, but you know, here it is. Okay, great. So now we actually have your velocities, right? What are we going to do right now? We're going to find our Lagrange, right? Or total kinetic energy of the system is equal to 1 over 2 multiplied by m1, mass of the first thing, multiplied by what? So v g1 x squared plus v g1 y squared, right? This is the velocity of the first link, kinetic energy of the first link, plus you have to do the energy of the second link, right? Might make it more simple if you just click T1, right? Kinetic energy of the first link, and let's actually find the mass is m1 and then m2, and let's actually call m1 and m2 as moment of inertia, rotational moment of inertia of the two links. So we're good. So let's do T2, 1 over 2 multiplied by m2 multiplied by vg2x squared plus vg2y squared. Okay, so your total kinetic energy is equal to T1 plus T2. Okay, now let's look into the potential energy. What is the potential energy of the system? Well, we know potential is equal to mgh, right? So m1 times g times what is the height of the first one, right? So we're gonna define a datum, right, or a reference, which is starting at this origin. Well, what is the elevation of this point, assuming g is actually acting downward? It's going to be, so you're going to take the homogeneous transformation, right? Or it will basically be simply yg1. We already have it, right? So multiplied by yg1 plus m2 multiplied by g multiplied by yg2. Okay, so basically now we actually have our potential energies, right? So what I will do is, well, we have this, we still need to basically put our gravity, right? Okay, next step is basically we have to, so we have to basically write our Lagrange, which is a total kinetic energy minus total potential energy. Well, let's run that and then see what happens. Okay, so this is our Lagrange. So we can, so that's it. Let's just keep it like that. Well, what are we missing here? Well, we're missing the rotational kinetic energies, right? So as a result of rotating this rigid body, basically, because it actually has dimensions, right? Or simply because it actually has an I, moment of inertia, so we're actually missing something over here, right? So it's going to be plus 1 over 2 multiplied by I1 multiplied by what? So rotational energy of the first thing squared, right? So omega 1 squared. Okay, second link is 1 over 2 multiplied by what? Multiplied by I2, right? The moment of inertia of the second link squared now plus omega 2 squared. Is that correct or no? That's not actually correct. Why? Because when you are finding the kinetic energy, it has to be absolute, right? Just like the way we did these are actually absolute absolute velocity of the center of gravity, right? So the energy actually has two components. The kinetic energy basically has two components. One of the components is actually linear, which is the linear velocity of the center of gravity. So 1 over 2m, the velocity of center of gravity squared, plus the rotational component, right? So here I actually have to add omega 1 plus omega 2 squared. And the reason for that is because my omega 2 here is not absolute. So the angular velocity, or the variable that defines the angular velocity of the second link, is not actually measured with respect to a fixed frame. It is actually measured with respect to the first link. And that is why we actually have to have it like that. Okay, so now we have our velocities, we have our potential energy, we have our Lagrange. Now what we actually have to do is we have to actually solve the Lagrange equation, right? So quick recap, what is the equation of Lagrange? So we have d of dl over d. So I'm gonna actually come here. Okay, there you have it. So this is what we're doing, right? And then if you recall from last time, so the first term here is simply, right, the partial derivative. So here's what I'll do. I'm gonna do EOM1, or equation of motion of link 1. So equation of motion for link 1, EOM1. Okay, so we actually have to do this, right? What I'll do is, what is that term right here? So maybe I can call this one F1. Okay, let me call this portion F1. So F1 is actually nothing but diff of Lagrange with respect to omega 1. Pretty simple, right? Why? Because it's only the partial derivative of L with respect to omega 1, right? And then this is here the power of MATLAB to actually allow you to do this symbolically. So we're basically moving from time domain, where we're basically converting this differential equation of motion into more an algebraic equation, right? Like basically treating it as numbers, but as simple variables, not actually, doing anything more than that. Okay, so we're done with the first part, right? Now I have to do d over dt of function f1, right? Well, let's see what is f1 function of. So if we actually run f1, you will see that f1 actually is a function of omega 1, is a function of omega 2, and is a function of theta 1 and theta 2, right? These are your variables, correct? So this is f1 is a multivariable function of 4 variables, right? So here, let me actually write it here. So f1 is a function of what? Theta 1, omega 1, theta 2, omega 2, right? So if you want to do d of dt of f1, right? Let's call it like that. So, right, that's it, right? So d of f1 over dt is equal to what? So I have to, right? So I have this function, which is a function of 4 variables. What I have to do is, when I do diff of f1, right? So the first variable, with respect to what? With respect to theta 1, you multiply this by omega 1, right? So it's d partial derivative of f1 with respect to theta 1 multiplied by d theta 1 over dt, which is omega 1, right? So I can do this actually for all of them. D diff f1 omega 1. Now this guy is multiplied by what? Maybe you guys should pause the video right now and then see if you can actually figure out the answer, right? What I should multiply that by? I should multiply it by alpha 1, right? Plus diff of f1 theta 2, multiply that by omega 2, plus diff of f1 multiplied by omega 2 multiplied by alpha 2. So there you go. So now we actually have the first portion. So what is our second term? So we have our second term. So what I will do is I'm going to call it like that. So EOM1 is basically, so this whole thing has to be equal to 0, right? So it's going to be equal to df1 dt minus diff of L over theta 1, right? Minus T1, where T1 is actually the torque on the first link, right? So we said this Q1 is actually the non-conservative forces which are applied on a system, right? So T1 is the torque. I'm actually going to define it here again as a variable T1 and T2. So basically, there you go. We actually, very briefly, we actually captured the equation of motion in the first time. Let's run that. So we're good. We can run that. And then if you actually do that, you can actually, the equation of motion actually will actually have the acceleration, right? If I run that, you'll actually see that you actually have alpha 1, right? So what I can do now is, so this is basically nothing but, mx double dot plus, kx or plus bx prime if you have damping. So here I can actually solve alpha 1. I will solve EOM1 for alpha 1, right? So MATLAB will basically solve EOM1. This is like that. I think this will also work. Or no? How about this? Okay. Yeah. So this is basically the same result as solving this equation of motion for alpha 1. And notice basically you actually have it as a function of alpha 2. So there is basically dynamic coupling here, right? So the angular acceleration of the second link actually affect the angular acceleration of the first link. So let's actually solve it now, solve equation of motion for link 2. What I'll do is just copy paste that. And then just be careful what you change here. Equation of motion of link 2, EM2. So F2 is going to be, what is going to change here? Only omegas, right? So second link, I'm going to change simply omega with omega 2. And F2 actually is a function of, all of them. So sometimes it's actually not a function of all of them. Okay, no, keep it like that. So nothing is going to change here, right? So I'll just change F2, right? So sometimes if you are unable to check, if you don't know what variables is that function, you can do all of them, right? And then whatever variables are changing, right? Not the length, obviously, right? And then if it's not a function of, let's say, theta 1, it will actually, it will be 0, right? So we don't lose anything if you actually do that. So we're going to change F2 on all of them. So EM2 is equal to F2 TT, and then this guy is for theta 2, and then torque 2, and then alpha 2 is equal to EM2, and so for alpha 2, right? Okay, so there we have it. All right, so let's actually now come here. We actually have alpha 1. So now we solved it. So we're going to come here, we're going to write it. So this is my alpha 1. Let's actually find what alpha 2 is. Alpha 2 is that. Okay, so I think we're good here. So now basically you have solved the angular acceleration of the first link and the second link. So what I'm going to do here is I'm going to actually numerically solve this problem. So I'll just simply write a loop for r is equal to 1 to 1,000. Let's do it over 1,000 iteration. And so we actually have our acceleration. If you have, let's define some variables. So I'm going to call time to be 0. So before the loop time is equal to 0, I'm going to do a time step of 0.01, let's say. Let's actually give some values. So M1 is equal to 1, M2 equal to 1, L1 equal to 1, L2 equal to 1, and then G is equal to 9.8. And what else are we missing? Okay, we need the initial values for theta's, right? So initial values for theta, let's say this guy is starting theta 1 is equal to 0, theta 2 is equal to 0, right? So in that case, what would you have? Remember, so okay, it's fine. So if theta 1 is equal to 0, theta 2 is equal to 0, it means basically this guy is in a flat position, right? Theta 1 is equal to 0, you are in a flat orientation. And so you also need to know the initial angular velocities, right? So omega 1 is equal to 0, omega 2 is equal to 0. And let's also put alpha 1 is equal to 0 initially, alpha 2 is equal to 0, and then we have torque 1 is equal to 0, torque 2 is equal to 0. So these are like my initial conditions. Then, so as the loop runs, basically, I'm gonna actually add time, right? So so at every iteration, basically the time will increment by dt, right? When time increments, I'm gonna actually know my initial angular acceleration based on whatever values that I have, right? Why? Because my angular acceleration is a function of simply the previous angular acceleration. So for the first link, the angular acceleration is equal to the angular acceleration of the second link multiplied by all these dynamics, correct? Now, if I have alpha 1, I need to solve omega 1. So how do I solve the angular acceleration from, or how do I find the angular velocity from the angular acceleration? Well, you guys know that alpha 1 is equal to d omega 1 multiplied or dt, right? So d omega 1 is equal to alpha 1 multiplied by dt, or omega 1 is equal to alpha 1 multiplied by dt plus the previous omega 1. Correct? So this is my previous omega 1, this is my new updated omega 1. So this is numerical integration. Now I'm gonna solve the position. I'm gonna integrate omega 1, so omega 1 dt plus my previous omega 1. There you go. So now we actually have these. My alpha 2, so I'm gonna solve omega 2 is equal to alpha 2 multiplied by dt plus omega 2, and then theta 2 is equal to omega 2 multiplied by dt plus theta 2. So basically, there you guys have it. So now we literally solve our thetas. So we solve this whole system. Let's run it, see if you have any issues. There is no problems, right? So it's basically simply solving the system. And now we don't actually need those anymore. Why? Because we have already solved the system, right? So we use those initially. Okay, let's run it. Okay. Okay, we're missing our i's, right? So what is our, we have to put our I. I1 is equal to, let's put some variables. I2 is equal to 0.5. So let's do that. Okay, we're good. So it ran it pretty quickly. And now let's actually plot it, right? So we said I can simply plot a link as a line, just call it line. And basically here I have, x1, x2, right? We said y1, y2. And this in MATLAB, basically this plots a line with coordinate x1, y1, first point, and then second point is x2, y2, right? So what is my first point is the origin? 0. What is my, so x1, x2, right? So we have 0 and then 0, right? And what was the coordinate of the first point? Well, let's actually come back here because we need those, right? Just need some stuff here. I want to do that. And let's run it one time. And let's actually x of, we need x of O1, right? Do we have actually f of O1? No, we don't actually have. So put the first link. So to put the first link, we need to know HO1, right? So we need to know HO1. So this guy, right? So we actually have the coordinate of the second point, right? So the second point is going to be L1 multiplied by cosine theta 1. And this guy is going to be equal to L1 times sine theta 1. Okay, now let's look at the second link. What we need is, we need HO2. Well, we don't have HO2, but we can get it. And the way we can get it is we can say HO2 is equal to HO1 multiplied by, so we rotate about z by theta 2, then we translate about x by L2. Alternatively, you can simply multiply this guy by one more translation by L2 over 2. Let's actually do that. Okay, now it's trying to plot the link basically. By L2, so let's wait, this is HO2. So let's actually look into HO2, right? Let's actually see it. Simplify HO2, and there you have it. Let's actually plot line link 2. It's going to be what? So the first point of this one is going to be here, right? So this is the first point. And the second point of this guy is going to be this guy, right? This is its x component. And then this is the y component. Okay. Okay, so this is the first one, x1, x2, right? And then this is here, y1, y2. Okay, we're all good. So what I want to do is to be able to animate that. One of the best ways would be to actually pause for a little bit, and then just delete the previous one. Delete link one. Delete link two. So this will kind of give me the feel of an animation. Let's actually quickly run that. Okay, great. Looks like it's actually working, but it's the picture is actually scaling. So I'm gonna actually set up an X limit of, let's actually put -2, 2, and then let's put Y limit of -2, 2, so we can keep it basically square. Let's actually run that. Okay, very good. So you see, basically we have the full dynamics here, but then it's going unstable as a result of we don't have any damping. So what I would like to do is, let's actually set our link one line width 4, give it some thickness, and then color, let's make it blue. Okay, so this we can set basically the property of this object, which is a link, line width 4, color blue as well, blue. So what I'll do is, let me actually increase this resolution a bit more, and then there you go. So this is our system. Okay, we actually have the full dynamics going on here. Let's do something. Let's actually reduce the inertia a little bit, and let's, we can basically now do any sort of dynamic simulation on that, right? We can also, for example, we can reduce the second link length, right? So it is L2 here is 1. I can make that 0.5. 0.5, and we can actually choose the masses as well. Let's make it 0.1, 0.1. Let's run it. Okay. So what I will do is to be able to actually visualize that. So we need to actually add a little bit of damping, and the way we will actually do damping is, remember in Lagrange, it will actually be here, right? So we have minus our torques, right? So torques are already, right? So I put actually my torques. What I will do is I will simply put my torque, right? Do you want to actually oppose the velocity? So I'll simply do that. Okay, and then same thing for the second torque, right? So T2 is equal to minus 0.1 multiplied by omega 2, right? So this is basically like I'm adding basically damping to the system. And maybe add a bit more damping here. Okay, so just quickly running that, and I think, okay, so it's going unstable, and it's not because of the damping. I think it's going because, okay, so here, basically, this guy should be the torque, right? Minus T1 as a torque. But we actually define the kinetic energies, right, as T1. So this is actually wrong here, right? It actually has to be the torque. So I'm just gonna eliminate that, make it a completely free system right now. So we're gonna completely ignore any initial torques. But the problem is basically we have already calculated alpha 1 and alpha 2 based on this equation. So what we have done, oops, I'm gonna comment it up to the point where we can actually solve for alpha and alpha 2. But without the torque. So let's actually do that. So I'm gonna solve for alpha 1 and alpha 2, and then I'm gonna replace them down. Right? So what is my alpha 1? Is this guy. Copy that. And then I'm gonna come back here and go all the way down. Okay. Okay, so here you go. Okay, and add a comment next to it. And then my alpha 2 is this guy. So let's This guy is now alpha 2. Okay, I think now we should be good to go. So let's come here. So notice basically the code is actually kind of like two separate codes, right? Where we use the first one to actually obtain or solve the dynamics of the system algebraically, and then the second portion of this is to actually, the second portion of that is to actually numerically integrate the system. Okay, so no need for this anymore. So this is my alpha 1, right? So we alpha 1, omega 1, theta 1, and then we solve for alpha 2. Wait, so this is wrong. Okay, let me just fix it. So alpha 2, omega 2. Let's actually run that. There we go. So this is basically using what we learned in our course to be able to fully mess around with the dynamics of systems. And now basically we don't have any damping, so the energy here will be conserved forever, right? And so basically now this loop iteration now. So now you can basically experiment with that. What we will do later is when we do control is basically we can basically add torques to it and to this equation, and then you can do like proportional controllers or PID controllers on the individual torques, right? So the problem here is that this system is very sensitive to dT basically, right? And the way what you should do is you should actually solve the kinetic energy and then compare it to the potential energy and then make sure they are equal so that your simulation is valid. And then you will actually see that in our notes, right? So basically, like I'm reducing my dT and I'm actually posing for a little bit less than that. But MATLAB is not a real-time software, so there is a cost for actually running this. So that is why you don't see that actually running in real time. Let's actually do something here. Let's put our dT here and then run that. Okay, exactly. So it's not running in real time basically. That's the issue here. Let me just put some on and increase that a little bit here. There you go. Yep, so it's not fitting the previous figure. That's why you're seeing sometimes. But when you do that, the system may actually go unstable. Why? Because you're doing numerical integration. So as a result of the numerical integration, you'll actually have a drift, and ultimately you will actually end up with some errors in your analysis. So the solution will actually converge from the theoretical solution, shortly after you actually start your move. One last thing, you can actually add a grid to it by typing a grid on. There we go, and there you go. So you can change anything that you want here. You can change your initial conditions. I can change my omega 1, for example, right? And I can also remove the gravity. What happens if I remove gravity? What do you think is going to happen? Nothing is happening, right? So now, basically, it's like you're looking at this on a table, right? From a top view, right? Now you can imagine this thing is in a horizontal plane, and it's not moving. So I can actually give it some initial velocities here. So I can do 0.2 here. Right, so I'm going to give the first joint some angular velocity. So you see basically it actually starts to rotate, right? And it's rotating with a constant velocity, right? So there you go. So it's actually rotating with a constant velocity. Okay. The reason why it's slowing down is because of the computation of the code here, and I can also give omega 2 to be like -1. Let's run that. Right, so now there's actually dynamics, right? So this one is rotating, right? So as a result of what is actually happening between the various accelerations, it's doing that. Now I can bring back gravity and then study that like this. So there you go. All right, guys, any questions on that? Let me know. Like I said, I'm always available, for questions outside these. Just send me an email. I'd be very happy. We can set up a Zoom call and then answer any questions that you guys have on this.